Okay, so good afternoon. My name is Giorgio Giorgiani, and I'm working at the ERFM, which is the Research Institute on the Magnetic Confined Net Fusion at the CA Cadarache. And I'm going to present this talk on which is called Advanced Numerical Methods for Plasma Edge Simulation in Tokamaks. So I'm going to start from the motivation of the talk, and then I'm going to divide it so that the presentation is divided in two parts, because I've been actually working on two different subjects. The first one is the optimization of the inversion of the 3D vorticity operator in the code tokamaks 3x. And the second one is related to the investigation of advanced numerical schemes for plasma simulations based on non-aligned discretizations. So there are two different topics, but the motivation is in common. It is related to the need of having predictive numerical tools for simulating the plasma edge. So the plasma edge is the outer part of the plasma in a tokamak, and so it extends to the outer part of the core until and the strip of layer, which is the part the part of the tokamak where the magnetic lines reach the walls of the machine. So the importance of the plasma edge is related to the fact that the physics of the plasma edge control the performance of the tokamak. In particular, the performance of the magnetic confinement and also the heat exhaust at the chamber walls. So we need predictive numerical tools for the simulation of the plasma edge, and the code that has been developed in the ERFM is called tokamaks 3x. The two tasks that I had in optimizing this code were the optimization of the inversion of the vorticity operator, and the second one is a perspective study on the advanced numerical scheme based on non-aligned discretizations. So I'm going to start from the first part, the first topic, which is the inversion of the 3D vorticity operator. The physical problem essentially is the computation of the electric potential in the tokamak. The electric potential is given by this elliptic problem, and which is supplied, as you can see, with the Robin and Neumann boundary condition. And the solution strategy used today to solve this problem is to use a direct solver. So we use the library PASTIX, which is a parallel library which uses LU decomposition to invert the matrix given by the spatial discretization of this problem. So the problem in using this kind of approach is that the scaling of with the number of grid points is very bad. In particular, the flop scaling is n square, and the fill-in scaling of the factorized matrix is n to the power 4 divided by 3. So it means that, for example, for very large cases, we are obliged to use this hypothesis of isothermal plasma, which allow us to factorize the matrix just once at the beginning of the time iteration, then keep the factorization for all the simulation. And for very large problems, we have to use a lot of resources on supercomputers. For example, for this grid, which has 16 millions of unknowns, the number of non-zero of the factorized matrix is about 10 to the 11. So the solution to this problem is actually to use iterative solver to compute the solution of this diffusion problem. So what is the problem of using iterative solver to invert this thing? Is that we have a strong anisotropy. In fact, the ratio between the parallel diffusion and the perpendicular diffusion is about 10, at least 10 to the 5. We have, sorry. So we have also this Robin boundary condition, which is kind of nasty because the Dirichlet part is very small compared to the gradient part. And finally, the grid is not aligned with the diffusion tensor, which introduces some extra term in the discretization, the spatial discretization. So all these facts produce some matrices with very high condition numbers, and so very slow convergence rates with the iterative solvers. So we have to design a specific solution to solve this problem. So I'm going to show you the approaches that we have considered so far, and so what the state of the art now. So the first one is an in-house solution, which is simply a preconditioned GMRS, but the idea is to find an efficient preconditioner based on physical insight of the problem. So to do that, I've wrote a MATLAB model without curvature terms. So I did some parametric tests using different kind of preconditioners, and in this graph, you can see that for a small mesh of 32 points in each direction. For example, this green line can be taken as a reference because it's the ELU0 preconditioner, which is the most common kind of preconditioner that you can use in GMRS. And you can see that for very high parallel diffusion, the number of iterations to solve the problem is about 300 iterations for this small problem, which is completely unacceptable. And but we have identified this precondition, which I called P9, which has little number of iterations, and moreover, they are kind of constant with the diffusion, the parallel diffusion. So we have implemented this GMRS in TOKAM 3X, and we are using PASTIX to perform this GMRS solve, because it has also this iterative refinement module. And we are waiting for, we have a minor problem on the interface between PASTIX and TOKAM 3X, so we are waiting for the Bordeaux team to fix it and to test this preconditioner. The second approach that we are trying is the use of the AGMG solver, which is an algebraic multigrid solver. So it is already implemented in the serial version in TOKAM 3X, and we have some nice results so far. For example, for this matrix, for this case, we got it's 2 million unknowns. We have a solve time of 130 seconds on one single node, but we were using a tolerance which is very strict, which is not at all the tolerance that we will be using in the real computations. And it's something that we have to also check, what is the tolerance that we need to have a result which is acceptable from a physical point of view. As a comparison, with PASTIX, the factorization is not, so it gives an out of memory on a single node, and the estimation time was 1400 seconds. So I think it's a promising result. Then the last one is the use of the MAFIS solver, which is an hybrid direct iterative solver based on domain decomposition. I think we will have a poster on that later. It's already implemented also in TOKAM, and the first results are quite promising, maybe slightly lower than AGMG. For example, for the same matrices, we have a solve time of 120 seconds, but using 256 cores. So this is the state of the art for this part of the research on this topic, and so I will pass now to the second part of the talk, which is related to the investigation of a new numerical scheme for the plasma simulation, which is based on non-aligned discretization. So the idea were to have a new scheme with this characteristic. So we wanted an accurate description of the geometry, some flexibility with respect to the magnetic field, with the possibility also of varying the magnetic field without the need of remeshing at each time step, which allow us to perform consistent simulation and also to simulate some tokamak operations. And finally, last but not least, we would like to have a computationally efficient scheme, which means on one end to reduce the number of degrees of freedom of the computation, and on the other end to optimize the parallelization aspect. So we propose to use this high-order hybrid discontinuous Galerki scheme, HDG, on a structured non-aligned mesh. So I'm going fast on this part. Discontinuous Galerki methods are finite element methods based on discontinuous solution element by elements, and the good characteristic of discontinuous Galerki method are that they give stable and robust schemes. We don't need to introduce stabilization terms in the weak form. They are highly parallelizable, and we can also do very easily adaptivity. With the unstructured mesh, we can define very easily the exact geometry without the need of refining. For example, here, if you can see that with the use of curved element, I can describe this curved boundary without the need of refinement. And then we can also we can deal with any magnetic configuration. In fact, there is nothing to do to consider X points like in this case. Here you can see that we don't have anything to do to consider these X points because the mesh is completely non-aligned. And we can compute up to the center of the machine. Of course, we have to use high-order discretization, because otherwise we will get numerical diffusion. So here is, so I developed this HDG scheme starting from a very simple model. So I took a 2D axisymmetric model, isothermal, so the only two unknowns are the plasma density and the momentum. I implemented high-order discretization. I coded it in Fortran with MPI and OpenMP parallelization, and it's linked to this library for the linear algebra. Then here you have the verification of the code with the manufactured solution. You can see that we get the correct order of convergence for all the polynomial degrees that we consider. Here is a validation with the code SolEdge, which is a very well-established code for this kind of computation in the plasma fusion community. And we have shown that we can compute until the plasma center, and finally we can deal with the solution with very low diffusion and also shocks. So, and we have just submitted a paper on this work. So finally, we have taken advantage of the fact that this scheme allows to have discretization non-aligned. We use it to compute some solution varying the magnetic field. So this is a work done in collaboration with the area Sofia Antipolis, And the final goal of this one is to have complete a complete coupling between the computation of the equilibrium and the transport. So here I'm going to show you the magnetic. These are the isolines of the magnetic flux. So I'm going to show you a movie where you can see the magnetic flux that moves in the machine, and we can study the plasma response at different transition speed of the. This is a transition from the limiter configuration to the X-point configuration. At the plane with the speed of this transition, we can study how the plasma respond to the movement of the magnetic field. And we can also, for example, study the heat flux at the walls during the transition in the two cases. So to conclude this, and we have written a paper also on this subject. So to conclude this part, so we have developed an HDG scheme, high-order scheme for a reduced plasma model that works on a structural grids. We have very good results on static simulation, and we also show that we can compute evolving simulations that open the path to consistent simulation, equilibrium, and transport. So the next step will be to introduce the electron and ion temperatures, to have a closed coupling between equilibrium and transport, because so far we just move the equilibrium and we compute the transport given the equilibrium. And then we would like to extend the code to the 3D. And so to conclude the presentation, I have shown you the two tasks of my research in the ECO project. So the first one was the optimization of the inversion of the vorticity operator, the three solutions that we proposed, precondition GMRS, AGMG, and MAFIS, and then the investigation of this new numerical scheme with this new characteristic, accurate geometry description, computation up to the center, and variable magnetic fields. Thank you.
So you mentioned that HGG is highly parallel, so you
Highly parallelized.
you parallelize
Yes, it's
the code.
yeah. I mean, I'm not an expert in parallelization, but the code is it's parallelized with an hybrid parallelization MPI, OpenMP.
And so you use a static condensation on
Yes, of course. Of the interior nodes for high order elements. Yes.
What is the generation of the material? You have perfect
Yeah.
coupling of the domain. These are high order elements.
Yes.
That is something that is.
It's done in Barcelona. It's the Lacan code. It's easy for you. You know it.
I have some idea. I haven't used it.
It's
But this is under development.
the
Not closed.
the name of the code is easy for you. It's not that. It's the name of the code is easy for you. It's a mesh generator which is done. It was done in the laboratory where I did my thesis, that you know very well. So. Xavier Roca worked on that.
The pressure ratio.
Yes.
But you are using it for complex solutions. No problem.
Yeah, of course.
and perform scalability tests?
No, I didn't.